Matt, who are going to be talking about the top 10 web hacking techniques of 2014.
Cool. Hi, everyone. So, how many of you have seen a version of this talk before? Top 10 web hacks of previous years. A few of you. You don't count. You work with us. So. Okay, cool. So, for those of you who don't know either of us, I'm Matt Johansen, and can you guys hear me? Is my mic on? Yeah, we're good. I'm Matt Johansen. I'm Director of Security Services over at White Hat Security.
I'm Johnathan. I'm a manager for the Threat Research Center. I head up our EU operations in the UK.
So he has a shorter flight, so he's going to be more lively because I'm jet lagged. So for those of you who haven't seen this before, we don't have a little clicker thing, do we? Oh. Right. So the gist of the top 10 web hacks is to pay homage to just the crazy amount of web application research that goes on throughout the year, and just trying to squish it into one talk. Most of these things that are on our list have their own hour-long talk. Is anyone in this room that has something on this list that they know about? Because I know some of the people on this list are from the EU, so I haven't met them before. No? Okay, cool. Well, if you see your name and you don't know that you're on this list, throw something so I can bow you or something, because we're gonna talk about your research. So yeah, we've been doing this every year for about 9 years or so. So this is the kind of the lay of the land for the top 10 for a very long time. So how this works is we take submissions from the community for best new research techniques of the year, right? Just open blog post, and we get anywhere from, we had a low year last year, but anywhere from 30 to 80, as you can see, total submissions. And then what happens then is there's a community vote that narrows that down to a top 15. And then we take that top 15 to a panel of security experts, like Troy, who was just doing the keynote, was on our panel this year. And that panel of experts narrows that 15 down to a list of top 10 and helps us order them and so on and so forth, right? So we can see, you guys probably recognize some of these names of attack web app techniques over the past couple of years, and we see slowly encryption taking over the king slot every year, right? With padding Oracle, which was then, of course, a similar technique used in Beast and Crime. And then last year, Mutation XSS took over top slot by Mario, who's going to talk later today. And yeah, so XSS took top slot again, but 3 of the top 5 were still encryption related, so people still really like encryption. So without further ado, I guess, microphone's off. It's in here. On. Better? Oh, okay, cool. Sorry. So without further ado, I guess, right, here's the top 10 of this year, right? So encryption is king again, right? I don't think any of us are surprised that Heartbleed took number 1 here, as it was probably the most echo chamber escaping web app thing to happen in the last decade, right? You know it's bad when your parents are calling you and saying, hey, should I be worried about this? I saw it on the news, right? That's how you know, okay, something serious went on, right? And so basically what we're going to do is we have nowhere near enough time in 45 minutes to talk about all 10 of these. So we're going to kind of give you just the fly through of 10 through 6, and then we're going to kind of deep dive into the top 5 a little bit more, right?
Cool. So starting with number 10, we have covert timing channels. Now, covert timing channel is essentially a side channel attack, or a timing attack where the measuring of how long it takes a system to process instructions may provide a malicious user with some privileged information. This particular research was covering various HTTP cache headers, and the time that was required to infer if data were either cached or not cached. So they looked at the last modified and ETAG response headers, and for request headers, did analysis on if modified sense, if unmodified sense, if match, if non-match, and if range. A lot of heavy math going on in here, but they made our top 10 list.
So that was actually the interesting thing about number 10. That was the first time we ever saw someone campaign to try to get onto our list. They actually put out a slide deck on SlideShare and said, this is why you should vote for us to get on the top 10 list. I guess it worked. They got number 10, right? So number 9, this one's kind of interesting because it was, distributed denial of service isn't exactly a new technique, right? But the avenue of attack was certainly unique. This researcher actually was able to put a DDoS attack within Facebook Notes, like the Notes application part of Facebook. They were able to launch an HTTP GET flood. So the DDoS attack was actually originating from Facebook.com. So that was pretty interesting.
So number 8, we have a remote code execution for struts2. This is a nice struts2 0-day, resulting in the manipulation of the class loader and it being able to allow you to basically pop remote code execution. So what you would do is you would pass the class.classLoader commands as a parameter to a .action resource, and then pretty much it would run whatever code you wanted to. So funny thing about this is that the original fix was to simply block class.classLoader. However, you could convert that to a bracket notation and easily bypass the first one. So they fixed that. And then again, they weren't checking case sensitivity. So the .classLoader portion can be lowercase c or uppercase c. So once again, the vulnerability is opened back up again. Eventually, this text down here in red at the bottom is what needed to be added to the exclude params portion of struts2 in order to seriously fix the vulnerability.
So this guy got, I think, 3 total CVEs out of it, because he got a CVE every time they fixed it, but not good enough, and then he resubmitted it, and it was a new CVE, and then he resubmitted it and got a new CVE. So 3 CVEs on the same bug for that one, so that was pretty cool. All right, so number 7, Google two-factor auth bypass. So this one was kind of just, this was another unique one that made the list this year, because this isn't attributed to any one actual researcher, right? This is anonymous hacker, ooh, right? But this one, again, made the news a ton, and we decided to still let it qualify to be on the list, and I'm glad we did, because it got voted, pretty high up. This was just an overall theme of we saw these two-factor auth bypasses more, this giant uptick in them in the past year, specifically targeting people like journalists who were starting to use two-factor auth, which is of course a great thing, right? Finally we're getting journalists to, use two-factor auth in their social media accounts and things like that, but we also saw them get bit pretty hard if they were able to bypass. And the one that actually, the post that stirred up a bunch and had an article in Wired and all this kind of stuff that was the reason this made the list was the bypass was actually through the cell phone carrier providers. They were actually social engineer, call the cell phone provider and social engineer their way into adding a call forwarding and text forwarding number to the account. And so if they were using text SMS-based two-factor auth, and there was some sort of SMS forwarding going on, they were able to steal the token and bypass that.
So number 6 is hacking PayPal accounts with one click. This is essentially just a glorified CSRF. And I'm really happy to see this one on here because this is the first time that one single bug bounty has made our list. Typically they're new hacking methodologies, but this one was really cool because basically what Yasser Ali found here is that when making an authenticated request to PayPal and stripping the session credentials or authentication tokens, you'd be redirected to a login page, okay? Now, CSRF protection was in place for this particular app. However, they were not regenerating CSRF tokens. So once you had it once, you'd have it for that particular user. What he found is that if you put in a victim's email address, so you have a known victim's email address as a targeted attack, and a false password, submit the form, in the response, the CSRF token that was generated was now associated to that particular account. So once you have that one token, then everything within the constraints of CSRF are applicable. You can just chain CSRF along with the same token because the app was not regenerating it. This is cool because it's the first time I've ever seen a way for you to the CSRF token was tied with your account, with your username for some reason, reasons. And they awarded him a $10,000 bug bounty for this. So I'm really happy to see a bug bounty make this top 10 list. I'm a bug bounty hunter myself, so kudos to this guy.
Yeah, that CSRF token lets you do absolutely anything on that PayPal account, right? So it was pretty bad. Okay, so number 5, we're going to get into a deep dive here. Did anyone hear about this one? Did anyone see this talk last year, this misfortune cookie research? This was some of the coolest research. This is probably my favorite one on the list, so even though it's not number 1, this one's close to my heart. So these researchers were able to actually attack residential gateway routers with a single HTTP request. And the way that they went about it is really cool. If you're interested, I'm going to give you a rundown. If you're interested, go watch the full talk. It's one of the best talks that I saw last year. You already did? Sorry. So just a little bit of background of what you need to know to actually understand this attack. These are things that I didn't really have a full grasp on at all. So how many of you have heard of this TR69? This was new to me. Yeah, it's new to most of you too, a few of you. Okay, so What this came out, this is the protocol that's used, or which it came out in like 2004. And really what this is the, it's also known as the CPE WAN Management Protocol, right? So CPE is Consumer Premises Equipment, right? So this is how your internet service providers are accessing your home routers and then doing something, right? You ever call your ISP and say, hey, something's not working, and then all of a sudden they send some sort of reset code and it power cycles your device at home. This is the protocol that's being used there, right? So these researchers looked at that and said, hey, that seems pretty powerful, right? There's a lot of power going on that the ISP has to control your device and your prem, right? So what's going on here? And so what is going on is there's this auto configuration server, this ACS server, that the ISPs use to have some semblance of dual authentication, meaning the ISP knows that you're actually the consumer that it's trying to talk to, and the consumer knows that you're actually the ISP that it's trying to talk to, and there's some back and forth communication there. But like I said, this was written in 2004, and this protocol actually just uses SOAP RPC, which is just XML over HTTP, right? So, this is a web hacker's dream, right? Okay, cool. So it's using HTTP, it's got control over the home router, okay, and this ACS is the all-powerful device that we're going to be worried about, right? So they looked at this, they said, that's a single point of failure, I'm going to focus on this to do my research, right? So they did a little bit of digging, and they noticed that this protocol uses port 7547. And doing some more digging and looking at some research from, I think this is University of Michigan, when they scan the entire internet, this port is actually the second most common port open on the entire internet, besides, of course, 80, right? And so, okay, this is widely prevalent. There's a single point of failure. Again, this dream just keeps getting better, right? Yeah, this was a scan of about 2.1 million devices, and so they said, okay, if we extrapolate this over across this number, if we can assume this is correct for the entire internet. They actually didn't have to assume, because Rapid7 actually did a scan of the entire internet later after they started their research, and the number was actually worse than this. It was 1.18%. So 46 million IoT devices had this port open, okay? So what's on this port? What's running on this port? So this is a breakdown of the technologies running on this open port that is open on 1.18% of the entire internet. And so, again, as researchers, what are you going to hone in on? The big chunk of the pie over there, ROM pager. So 52% of these open ports were running ROM pager. Dug a little bit deeper, said, okay, what versions of ROM pager are there? What kind of versions of this code do I need to hack on in order, if I want to take advantage of some of this software? Turns out that 98+% of the ROM pager versions that were out there were all running the same version. Anyone want to take a guess at what year that version was written? Oh, wow, no. that'd be scary, 1990. No, it was actually 2002. So, really up-to-date version of this software. It was roughly 7 versions behind. And it was, 98% of that 52% of 1% of the internet, right, if you wanted to do the percentages back. So it's a ton of devices running the same version that's an old version of ROM pager. So let's get to the hack already, right? So that's kind of the breakdown of what's going on. Why do we care? So this ROM pager version, on router firmware, these researchers decided, hey, let's fuzz this stuff, this specific version, because it's everywhere, right? And pretty quickly, they were able to crash the router, right? They, with some HTTP header fuzzing, they added the authorization header, a quick digest username parameter in 600 A's, and the router crashed. The problem was there was no debug interface for this router whatsoever, so they couldn't really get a core dump and kind of do all the cool things necessary to figure out what kind of overflow situation they had, right? But for those of you familiar with this kind of research, this is the bit of code that was vulnerable there, this unprotected string copy. So I just wanted to include that there real quick. So this is this is probably the coolest part of this talk that these guys gave. Since there was no debugger available, that they couldn't get the core dump and couldn't figure out what they did to crash the router, they actually opened up the router and soldered into the motherboard and then wrote their own debugger, which is the most hackery thing I've ever heard of, which is awesome. And then to make it even more awesome, they named it Zordon for any of you Power Ranger fans. It's a forced acronym. I can't remember what it stands for, but it is called Zordon. So this is what the output of their debugger, once they crashed the router, this is what it looked like. And you could see an instruction pointer up at the top, and they were like, okay, we need to overwrite the instruction pointer and do some nasty stuff to this router. The problem was this wasn't reliably exploitable over the internet, because even though it was the same version of ROM pager that was so prevalent, the memory stacks, depending on which firmware was using, which device it was using, was a little bit different. So you couldn't reliably exploit this, this exact point in memory that you would need. So they had to take it a little bit further. Well, ROM pager happens to use cookies, for infinite valuable reasons, right? So, but the way that their cookies are laid out is pretty interesting. So they have a pre-allocated, namespace, and it's really just C0, C1, C2, whatever. And that array is actually pre-allocated in memory. So now across devices, they don't need to worry about the different memory stack, because this array of cookies is pre-allocated, so they know exactly where it goes. In the infinite wisdom of ROM pager, the pointer in memory that was used was just strip the C off of the cookie. So if you have cookie 0, that was the pointer 0, right? Cool. So that made it infinitely easy for these guys to just write some malicious cookies and completely just remote code execution on all these routers. So here's a screenshot on the bottom of just a benign example, right? So if you just change the name of the cookie to C and then whatever you want the instruction pointer to be, that instruction pointer just changes the path into, oh my God, lead hacks, right? Because that's what you change paths to when you're trying to POC something. And it would just redirect the browser to this, this slash whatever, right? So this was the only instruction pointer that they actually put in their talk, I think because the other ones are too scary. On stage, they didn't show the actual array of cookies that they used, but just with setting, I think it was 3 cookies, they were able to completely bypass authentication of the router. They could flash the firmware if they wanted. They could do whatever the heck they wanted, right? So again, this was for residential gateway routers, so this owned all the computers behind an entire neighborhood. I think there was 189 countries, and in some countries over half of the IP addresses were vulnerable to this. So it was not a small bug. And this is usually the slide where I say, and here's the warm and fuzzy part of why you shouldn't be worried, but this one, I don't have a warm and fuzzy, I'm sorry. The warm and fuzzy for this room is you can, if you're using a vulnerable device, you can flash your firmware, right? And people in this room probably can figure out how to flash your firmware, but don't give, grandma my phone number when you're trying to walk her through flashing her firmware, and I'm not gonna hold my breath while my ISP updates any of their devices that they have throughout residential gateways. So this one's kind of scary, but these guys are maintaining a list of vulnerable devices there for anyone who wants to check it out.
Okay, so moving on to number 4, we have the Rosetta Flash tool. Now, this made a lot of headlines last year. Is anyone familiar with this by any chance? Or heard of Rosetta Flash? A couple people? Cool.
Is he in the room? Yeah.
Oh, everyone give this guy a round of applause. This is freaking awesome. It's fantastic. So he's got a much more in-depth talk about this. I believe it's at 15:30 today. Yeah, so definitely go to him for the deep dive. We're not going to do it justice by just skimming over it.
Congrats.
Yeah, that being said, so what this is this is a tool that he created to convert a binary SWIFT into a non-alphanumeric SWIFT that can then be executed on a target domain site. It's using JSON-P. So just like we said right there, we'll have some binary information. Yeah, this is all credit to him, by the way. So you have some binary SWIFT. Everyone's seen this like binary garbage before. And his tool essentially uses Huffman coding to act as a Rosetta Stone to translate that information into readable alphanumeric text. This is awesome because of JSON-P. So how many hackers have been like hacking around and you see a JSON-P response come back with a callback? Yeah, we see it all over the place. So JSON-P accepts a callback parameter of values uppercase A through Z, lowercase a through Z, an underscore, and a period. So although there's a little bit of input validation in place, you can't pass it a binary input because obviously it's not going to work. But if we take the Swift file and then convert it to just alphanumerics with those allowed character sets, we can force JSONP to execute the Swift as if it's hosted on a target domain. Now, just a couple of sites were using this, or are using this: Google, Yahoo, LinkedIn, Twitter, GitHub, And when we say Google, it's not like some third-party acquisition that was acquired 2 months ago. It's www.google, accounts.google, maps.google, like all the juicy stuff. So here we have just a brief overview, again, of the research he's going to go into later. Just a binary breakdown of normal Swift header. Now here we've got uncompressed Swifts, zlib compressed, and LZMA compressed Swifts. Now for the purpose of this research, we're just going to focus on the zlib compressed header. And this is due to the fact that he was able to brute force the Adler32 checksum at the end of the data that verifies the integrity of that zlib data section. See, all of them start with a magic byte to determine which version it is, then a version, file length, and then break up depending on which type of compression or no compression is used after that. So Rosetta Flash is going to use an ad hoc Huffman encoders in order to map non-allowed bytes to allowed bytes, because we're going to have a lot more in the character set of binary trash, if you will, than just alphanumerics with those special characters. So we don't have time to go into all the technical details of this, sadly, but the ways of getting valid characters for the first 2 bytes here, as well as the Adler32 checksum, is kind of involves some deep math that he dives into.
1530.
Yeah. So again, this is the proof of concept that he generated. So just some little action script right there on the left. This is how it would convert into a non-alphanumeric translation. And then you can exploit that, if we can see this right here. Swift files can be embedded on an attacker-controlled domain using the content type forcing object tag. So you can see that we have vulnerable.com in the attribute value for data. And then down there at the bottom, in the param values for flash vars, we have the vulnerable site that we're attacking that uses a JSONP callback, as well as an attacker host or attacker supplied resource, if you will, to log data that might be traveling through it. Now, mitigations for this. One, you could just not use JSONP at all or sandbox that particular information off. 2 other things we can do with headers, though. We can set a content disposition attachment file name, which is going to then download that Swift file instead of render it in the browser. You could also change X content type options, no stiff, or add that, rather, because then as long as the response header doesn't come back with X shockwave flash, it'll come back with application JSON or application JavaScript, then it's not going to fire as valid Swift. Also, the quick fix, if you will, is to just add a block comment section down there in a little green text in front of the callback in the JSON. This is what Google, this is what GitHub, Twitter, all of them are doing to remediate this very simply. So if you're actively hacking around and you see this now in your callback responses, then that's basically where it's coming from. It's a defense to the Rosetta Flash attack.
Is that still in your Twitter bio? // // I saw that in his Twitter bio for a while. Yeah.
Kind of.
That's fixed. Yeah. Okay, cool. So yeah, we flew through that because he's here and you can see that if you're
Get the deep
interested,
dive
right?
from him.
So, okay, number 3, we have Poodle. So this was the year of the branded vulnerability, right? If your vulnerability didn't have a marketing team, then sucks for you because these guys did, and so they got on the news. So everyone heard about Poodle, right? And then there was Zombie Poodle, and then there was like Poodle Bleed or something like that. There was all sorts of versions of this that just kept rearing its ugly poodle head. But let's kind of go into what made Poodle what it was, right? Why was everyone so scared, right? So, we had to leave this slide in. Usually we give this talk to, not necessarily a full AppSec crowd, so we kind of have to, okay, what's SSL, right? So SSL is magic, and it, takes some plain text, it squishes it with a key. Whereas Troy, base 64 encrypts it or twice or whatever, right? And then we get a ciphertext, right? No, that's on video. Crap. I just said base 64 encryption and it's recorded. So, okay, so just a quick rundown of the vulnerable version of SSL. So the vulnerable version of SSL for Poodle was SSL version 3. I'll play my favorite game of the talk. What year did SSL 3 come out? Anyone? I forget. Where is it? It's on the notes.
Long time ago.
In the 90s. Yeah, that's closer to your, I think it was 96 or 98, right? So it came out a long time ago, right? TLS replaced it in the 90s, and then TLS 1.2 came out in 2008, right? So even TLS 1.2 is still, pretty old, right? So SSL version 3 is the vulnerable version that is going on. So we're going to give you a history lesson on how that works, right? So say you have some HTTP request, right? It's got some sensitive data. The first thing that happens in SSL v3 is there's going to be a MAC added to the end of that, right? So this is just to make sure that the sensitive data and the whole thing is tamper-proof. It's basically a checksum for the ciphertext, right? If the MAC doesn't check out, the request fails, and so that's how you know that it was tampered with. Right? And then after the MAC gets added, we have some padding that gets added. So the padding is going to vary in size depending on what type of encryption you're using. If you're using, DES is 8-bit, it's got to be a multiple of 8-bit, and AES is going to be 16-bit. So yeah, we throw this padding on here, right? The padding is important for this attack. That's kind of why I'm going through this. So the last character of the padding is actually the magic one, right? So the last character of the padding, what that does is actually tell you the size of the padding, right? So that's going to say, okay, how far back do I need to go when I'm decrypting this to get to the MAC, and then I validate the MAC, and then I get to the sensitive data, right? So this whole thing with the padding and the MAC, the sensitive data gets encrypted in SSL v3 using the cipher block chaining algorithm, which also was proved vulnerable by, which one was it, Crime or Beast or Crime Beast or whatever. So this is also a vulnerable algorithm, right? So this is one of the many ways this is vulnerable. So how cipher block chaining works is you're going to take this whole blob, it's going to break it up into groups, and it's going to exclusive OR them all the way down the line, right? So this is the encryption works this way, decryption works that way. This is the history lesson, sorry guys, right? So if the decryption works backwards, remember that that important character is that last one to tell you how long the padding is, to tell you how far you need to go back to validate the MAC. So that's important in this attack because the MAC failing and actually dropping the request is what helps the attacker iterate and tell if he's going to be able to be stealing actual sensitive data or not, right? So if, say you have some attacker man-in-the-middling you, and you're on an SSL v3 connection, what the attacker is going to do is going to take one of the CBC blocks from the sensitive data, so some early on CBC block. It's going to copy it and paste it over the end of the padding. So as we remember about that last character being important, it's going to overwrite that last character, right? So most of the time, what's going to happen here is that this request is going to drop, right? Like he overrided the padding, that means that the length character is wrong, and you go back and the MAC check fails, and then the connection just drops, right? But about 1 in every 256 times, just kind of lucks out, stars align, and the length is right, and we're all good, and the connection is fine, right? So if the attacker iterates this, say with like JavaScript or something, just a ton of these requests, and keeps just copying and pasting this over, what this allows them to do is each time that they get that right, they know that last character, they know what that last character is as part of that CBC block, which is encrypted sensitive data, right? And so if they keep doing this a few thousand times, they're going to be able to get a few characters out of the sensitive data, right? So everyone said, okay, well, what's the worry? Just don't let someone do a couple thousand requests, and even then, it's just a few characters at a time. What's the problem, right? Well, session cookies aren't always that long, right? So that's the kind of thing that we're worried about, and they're also predictably located, early in the sensitive data, right? So they know where that is. So being able to pull out a session token was, feasible. So this is the kind of thing that we were worried about during this attack. So the fixes are pretty simple and kind of silly to say at this conference. So it's just don't use one of the oldest versions of SSL out there. Just completely disable that. Of course, you're going to lose some Internet Explorer 6 users to your website. So I personally say sorry, like figure it out. If you are absolutely forced to use, to leave SSL version 3 enabled on your website due to some customer base somewhere being unable to upgrade their browsers, you can disable the CBC algorithm and use a different one, which will leave you vulnerable to other things, but it will fix Poodle. And yeah, that's kind of the remediation.
One side note to this, and it's kind of funny, because in about October of last year, Microsoft submitted a patch to IE6 that'll actually allow you to enable TLS version 1.0 on it, but you still have to go into like all your encryption settings to specifically enable it. And users that are using IE6 typically don't even care why that's important to use a particular version of TLS. Just
if you're using IE6, you don't know
there's
where the
other
settings
problems
are.
to worry about than encryption. So number 2, we're moving on to shell shock, or what's also known as bash door. So like you said, this is the year of branded vulnerabilities. When shell shock came out for a couple weeks afterwards, everyone thought that Skynet was going to take over, and this was how like the AI apocalypse kind of just starts.
The Ninja Turtle apocalypse, right?
Yeah. So it's extremely, extremely easy to exploit. It's like on a scale of 1 to 10, 10 being the easiest, it's a 10 on ease to exploit. The severity of it is also a 10 because it's remote code execution. One can argue that exploiting this is probably easier to do than explaining it to someone. It's that awesome. Because from a single request, a single unauthenticated request over the web, remotely, you're rewarded back with a shell, which as we all know is game over. So just to go into a little quick example of when this first came out, Arata Rob is a great guy to follow on Twitter. He did a lot of deep diving into this as soon as it came out. He's got this open source tool called MassScan, which people may or may not use for good or nefarious purposes. And so all he did here was select a target IP range to scan the internet with whatever ports. And in his user agent, cookies, host, referrer headers, and the request headers, he just submitted an object reference, which we'll go into later, and then a ping command to ping back to him. So what would you expect to see if you scan the internet with all this information and the shell shock bug was active? They're going to call home. Ping. They're going to ping you back. Now, although that's not really a hack, if you will, I mean, yeah, it is, but look at all these addresses that were pinging him back. And this is just from a quick scan. Like this could probably happen within like the first 30 seconds of scanning.
How many people follow him on Twitter? How many people saw this happen live? Just a few of you? You guys should follow him.
Yeah, he should get
on
like
Twitter.
100 new followers.
He's
He's a great guy to follow.
This was within hours of shell shock coming out, right? So this was kind of the, oh crap, that's real. Like, there's a lot of things pinging his server.
Yeah. So although there's nothing too troubling about just getting pinged back, it opened up the question: why did the server ping us back, and how was the ping command actually executed? Now, again, a little quick history lesson, but I'm not going to go too detailed into it. Back in a time before we had pretty user interfaces, everything was done by the command line. It allows us to ask questions like who's currently logged in, create new files, list content, show the processes, delete everything on my hard drive, yes, I'm sure, in just like 8 characters. Because, everyone should be able to use this. This is where the shell shock bug is. And the vulnerability lies in being able to arbitrarily define an environment variable which specifies a function definition. It's basically like command injection. What's going to happen here is that after that last curly brace on the end, Bash is going to continue executing code as if it were syntax and not a string. Now, in the sense of the web, Bash is extremely widely used. About 50% of web servers at this time were Apache, and Apache will process CGI scripts. CGI scripts are processed in Bash. So just by making a request to it, and it's analyzing, the referrer header or the user agent, if your injection is in one of those places, the code's going to execute just by making a request to it. So now the next question is, how do you get another system to run this instruction? Exactly that. We don't have to trick someone into physically typing in the command. You've got programs A, B, C, D, and E that are all talking to smaller programs, F, G, H, I, et cetera. Because that's what we do as developers. Instead of rewriting new programs, you use what's already out there. Like if I want to parse a file, I'm not going to write the parser myself. I'm going to use awk or grep or something that's already like that. A lot of these use the Bash shell to talk to each other in the background. Now, the purpose of this is that it's not limited to just web servers. Internet of Things devices, anything that's running the Bash shell is going to be vulnerable to this. If you have an autonomous Wi-Fi enabled dog feeder at home, it can be part of a Bash door botnet, if you will.
Or a light bulb, as we saw.
Or a light bulb, yeah, exactly. That's the thing. All these little microcontrollers, most of them are processing Bash. Bash is extremely old. It's widely used. It's well adopted.
Oh wait, we got to play my favorite game.
Oh yeah.
How long has shell shock been around? 25 years. This was vulnerable. 25 years, right?
Yeah,
so we can actually, the other funny part about shell shock is we can actually go and look at the thread where the researcher like disclosed, and he doesn't really quite grasp the seriousness of it yet. He just kind of says, hey, I think I found something, and I think it's been around a really long time,
Yeah.
and yeah, understatement in the security of the decade, right? Also, one of my new favorite T-shirts is "My user agent is," and then it's a big shell shock exploit that actually patches shell shock. That was I think the coolest exploit that I saw. It's, okay, run the commands that patches itself. That'd be the best worm ever, right? So
That would be awesome to see.
That's what I'm
like,
saying.
Whoever finds the next remote code execution,
It's very
make it
illegal.
with a patch. There's infinite e-fame right there. Okay, cool. So that's shell shock. Extremely easy to exploit, extremely easy to implement, and caused a lot of problems as soon as it came out. So moving on to number one, as I just previously went to, is Heartbleed. Another branded vulnerability, another game over, we thought the world was going to end type of vuln. A couple weeks go by, and obviously, we're all still here. Now, Heartbleed is a little bit different. It does share seriousness with shell shock and how severe it is. It's arguably easy to exploit, not as easy as shell shock, because just like a script kid, you can pick that up. What's going on here is in the OpenSSL protocol, there is a module called Heartbeat, the Heartbeat extension. And what the Heartbeat extension does is it stops you from having to have multiple simultaneous TLS connections going on at the same time. Because once you make a request to a server over SSL, the first thing that happens is the TLS negotiation phase. You know, they exchange keys, they talk to each other, and there's a lot of overhead by having multiple TLS sections once like a packet drops, et cetera. And we'll get to that here in a moment. So just real quick, a little background using some Netcraft statistics. Again, about the same time shell shock came out, about half of the servers out there were Apache, with Nginx slowly being on the rise. Now, market share of active sites, it's kind of like how this is. Microsoft IAS server was the third most used, but they use Microsoft's S-channel implementation of OpenSSL, which is not vulnerable to Heartbleed. That doesn't mean that if you're using an IAS server that everything's going to be fine, because you could still be using like an Nginx or HA proxy load balancer in between.
We had a ton of our clients, like what White Hat does, we scan websites for vulnerabilities, right? So we were letting customers know about this vulnerability, and a ton of them just said, well, no, that's our load balancer. That's not us. Can you get this off of our report? We have like an auditor coming in, and we're like, no, we can't take it off the report. Like, I don't know, call more times to your load balancing company. That's my remediation guidance, right? Like.
So here's the problem. A little bit of just introductory static analysis would find this. And it's funny, I believe this commit happened like at 11 o'clock on New Year's for like 2012. So whoever this developer was probably interested in like leaving and going out to drink or something. So yeah, just an insecure memory allocation here. Payload plus padding is taken from user input, no bound checks, no restraints. So we have user input making it directly into the buffer here. Now, what this does is this makes the size of the heartbeat response controllable, upwards of 64 kilobytes of memory. Now, so again, what happens here, which I kind of went on a ramble about earlier, the first connection you make to a website over HTTPS, a TLS handshake negotiation phase is going to occur. They're going to negotiate keys, they're going to say, hi, I'm the client, I'm the server, how are you doing? Boom, TLS connection is made. Now, if you have like a dropped packet or a little bit of lag, or you close your browser tab for some reason and reopen it back up, a new TLS connection is going to be made. And you can have multiple of these happening at the same time. So what that does is that creates a lot of overhead. It's computationally expensive. So the Heartbeat extension was made. Now, what the Heartbeat extension does is with much less overhead, basically let you know if the TLS connection is still alive. So you send a Heartbeat request, the response comes back, or the keep alive response comes back rather. Yes, you know that client's still there, keep the TLS session active. Now, the Heartbeat request is going to contain some request data. We've got a payload, and then the size of that data. And these are all both user-controlled values. For an attacker to exploit this, the request is crafted that contains a little bit of data, the payload, and then the size of that request, which we would craft to be arbitrarily large, because, again, it's controlled by the user. So we pick 1 byte to send as our payload. Now, although we're only sending 1 byte of actual information, we're going to say that the size is 65,536 bytes instead of 1 byte, because, again, we can control everything in this request. Now, server side, what's going to happen in server memory is that this information is going to get cached, and then you'll see in black there, P, which is the only 1 byte that I sent. And the rest of that random data is something within the memory bounds of the 64 kilobytes. When the keep alive response occurs, the payload of that same size along with whatever's in memory is going to be returned back. And that's it. That's all Heartbleed was. You can do this by sending an anonymous heartbeat request. You don't have to be authenticated. You don't have to be logged in. The server just has to be running that vulnerable version of OpenSSL. And I forget which site it was, but someone ran a contest as soon as this came out because it was taking a while for them to patch. And the contest was like, show us our SSL keys. And I forget who got it, but it only took them maybe like 4 or 5 hours. It was still billions of requests. It was a ton of requests because you're going to get a random arbitrary piece in memory here. And that's going to contain all kinds of stuff. It can contain user-submitted data, validated tokens, cookies, passwords, credit card information, anything that's in like a normal post request could be cached in memory. And because this kind of picks a random data, you just send the same request over and over again. You get back this 64 kilobytes worth of information, and then it's just like a puzzle. You just piece them all together. More importantly, you can get the keys to encrypt and decrypt traffic from the server. So if you happen to be logging information, you can go back and then use those keys to decrypt it if perfect forward secrecy is not enabled. Now, although that is a protection baked into SSL, not everyone uses it. And that's it. That was our Heartbleed.
So, before we get to our lessons learned here, Heartbleed also, the reason it's number one is that it's now the barometer, right? It's like the, is it as bad as Heartbleed, right? We just saw something come out yesterday. What was the name of this thing? It was like 2 days ago. Logjam.
Oh, Logjam, yeah. New TLS phone.
New TLS phone. And the barometer is, well, is it as bad as Heartbleed? Right? That's like what all the reporters are asking and stuff like that. So of course that one makes number one. And the other really scary thing is completely untraceable if you got hacked, right? So you just had to kind of assume compromise and assume that your SSL keys were stolen if you were vulnerable to it at any point, and then redo them. And how many people do we think did that? Right, so I'm gonna go with not that many. Okay, so we'd like to do a little lesson learned, right? So encryption is king. That's kind of what I said at the beginning, and saying at the end here, even though it wasn't the top hack last year, it's just widely respected research. A lot of the times, encryption research, things like Crime and Beast and we saw vulnerabilities we saw in the past take a very serious level of knowledge about encryption, right? Like, years of, most of the research was coming out of University of London from PhD candidates, right? So the community just wildly respects encryption research, and it makes the list every year. Privacy is more and more important these days as we see all sorts of, crazy government things going on, right? Creativity is also something that's really, really highly respected, right? So for any of you who saw this talk last year, it was one of the more creative bugs we ever saw was the pixel perfect timing bug. Was using some HTML5 video thing, SVG attack to completely bypass same origin policy. Great, right? So really creative stuff, and this year we see it a bunch again, which is things like shell shock. It's been around for 25 years. Someone just looked at something that's been around that long and just used it in a way that it wasn't supposed to be used, right?
Yeah, so shell shock's 25 years. Heartbleed was an implementation error from 2 years ago. SSL version 3 is 1998.
Yeah.
It's a downgrade attack, but that's still a vuln from 1998 software.
So this takes creativity. This doesn't take book smarts. This takes looking at something that's been under your nose for a really long time and figuring out how to completely own the internet with it, right? And then just overall web security prevails. Look at this conference, right? This is one of the biggest conferences. AppSecEU, AppSecUSA, they're just growing every year. Whenever you do see any sort of security news, escape the echo chamber of security and get on to like actual news websites like CNN or anything like that. It's always web stuff. It's always like someone got hacked with SQL injection. Somebody got hacked via some website. Some social media account got popped and the stock market dropped immediately or something like that. It's just ridiculous, right? And it's all web security, right? So, you guys are at the right conference to learn a lot about this stuff. So we just want to thank our panel of experts. Troy is here. I'm going to buy him a beer. And just thanks to anyone, if any of you have submitted anything when we do open this community aggregation of research, and then any of you who voted to narrow it down to the top 15, thank you guys. Now that you guys have all heard it, I'm holding you all to it next year to submit and vote. And just thank the researchers who just continue to do mind-blowing stuff like our JSON-P friend over here. You can go check out later, and all the researchers the rest of the day. This you know, it's the reason we're all here. So thanks, guys.
Yep.
We don't have time for Q&A because we're running a little late, so we'll be around the conference the next 2 days, so just track us down.
Yep.